Welcome to Module 8, the digital sound. So in this module, we will explore how sound is digitized and processed, covering topics like signals, sampling, quantization, and Nyquist theorem. Don't be scared about it. This concept formed the backbone of modern digital audio system that we use today. But let's go back to the signal. What's a signal? A signal is a physical quantity that varies over time and space to carry information. So from the mathematical point of view, a signal is nothing more than a function which is dependent from three variables, x, y, and t, where x and y represent the space and t the time. So the signal is a quantity that is dependent on space and time. The basic formulation of sound signal takes into account only their dependency on the time, which is t. So a sound can be expressed by ft. So for example, if we would like to create the function related to a signal sinusoid that produces a sound, we can express it like ft equal to a multiplied the sinusoid, so the sin, for b multiplied t plus phi. We already have seen this formulation. So now signals can be analog or digital. Analog signals can assume any real value within a given range and are basically time continuous. In contrast, digital signals vary within a finite set of discrete values in discrete time step. Sound, being continuous, must be converted to digital form for storage and manipulation. This conversion process is called digitization, and it involves two main steps, the sampling and the quantization. So let's delve into the sampling process. The sampling involves measuring the amplitude of a signal at regular intervals. It's like to have snapshot of the signal, of the sound signal, at certain interval. The sampling rate measured in Earth indicates how many samples are taken per second, and the sampling time is the time between two consecutive samples. For example, if the sampling time is 0.001 seconds, so the sampling rate is 1 kilohertz. Of course, it's intuitive that the higher is the sampling rate, the more accurate will be the captured original signal. And now let's move to the second part, the quantization. The quantization assigns discrete amplitude values to each sample. Quantization, in other words, leverages a grid constituted by a certain number of discrete values. So the signal amplitude value are then assigned to the closest discrete value on the grid. Again, the number of steps in this grid is related to the number of bits, and which is called quantization bits, that are basically used for the numerical representation. So for instance, if we use 3 bits to represent a sample, allows only to have 8 quantization levels. 2 power 3 is equal to 8. It is intuitive that the more levels or bits are used, the higher the resolution and fidelity of the digital signal. But this also increases the storage requirement. So we have a problem here. So to summarize, the digital conversion of an analog waveform depends on sampling and quantization parameters, which are the sampling rate and the quantization bits. For sampling, the higher is the sample rate, the better is the approximation of the original curve. For quantization, the greater the number of levels, the higher the fidelity of the reconstruction, but also the number of bits needed to represent a sample. The bit rate generated by a digital audio signal can be computed by multiplying the amount of quantization bits and the sampling rate. So the bit rate is measured in bps, bits per second. Maybe you have already heard about it. For instance, a voice signal might use 8 bits and a sampling rate of 8 kilohertz. So the result in terms of bit rate is 64,000 bit per second, so bps. Let's provide another example. Let's consider an audio signal that uses 16 bits and the sampling rate of 44,100 Hz. And the result is a bit rate of more than 700,000 bps. So, as you can imagine, higher bit rates provide better approximation of the original signal, but require more storage. We will address this in next modules. And now move to the Nyquist theorem. The Nyquist theorem is very connected to the transformation from the analog signal to the digital signal, and states that an analog signal can only be faithfully reconstructed if during the transformation process it was sampled at a rate greater than twice its bandwidth. For example, let's consider the speech. The speech has a bandwidth of 4 kHz, so a sampling rate at least should be of 8 kHz. Okay, so let's move to the second example, the high-quality audio or music, where the bandwidth is of 20 kHz, which is basically the range of frequencies that we can hear as human. These require, according to the theorem, a sampling rate of at least 40 kHz. This principle ensures accurate digitization without losing important frequency components. So this is the frequency used in CD, for instance. Okay, on the other side, now let's consider the storage effort. And let's consider the example for it, the voice signal that we have seen before. As we have stated, there is a bandwidth of 4 kHz, and let's consider 8-bit of quantization. So the bit rate now is 64,000 bps. That require about 480 kilobytes for 1 minute of audio, which is not much. But now let's move to the stereo music. With a 20 kHz bandwidth, 16-bit quantization and 2 channels, so the bit rate now here is 1.41 megabps, requiring about 10 megabytes for 1 minute of audio, which is a lot. This calculation demonstrates how different parameters influence digital audio quality and storage needs. So let's move to the conclusion of this module. In this module, we have covered how sound is digitized through sampling and quantization, and the importance of the Nyquist theorem. These principles enable the creation and manipulation of digital audio systems, shaping how we experience sound in modern world. Thank you for your attention.